Hello everyone, my name is Alessandro Tognetti and I'm going to present my work on combining physics-based simulation and machine learning for electrical impedance tomography-based tactile sensing.
Electrical impedance tomography has been recently explored for building flexible and conformable tactile sensor. The structure of the sensor is very simple. We have a conductive substrate, the active area of the sensor, with a certain number of boundary electrodes. The principle is that a force applied on the active area of the sensor is associated with the deformation of the substrate, and this deformation implies a variation of the conductivity of the sensor material. So our objective is to estimate the variation of the material conductivity and to relate this variation to the applied mechanical force. So to perform this estimation of the conductivity of the material, we employ a tomographic-like technique in which we supply the boundary electrodes with electrical currents and we measure boundary voltages. So the structure of the sensor is very simple. There are no electrodes or rigid wires on the active sensing area, and this can enable flexible, stretchable and conformable tactile sensing. The main issue in electrical impedance tomography tactile sensing is that we need to solve the inverse problem to obtain the conductivity variation from the measured voltage at the electrodes. The inverse problem is nonlinear and ill-posed and has associated high computational cost. In classical electrical impedance tomography application, the inverse problem is solved relying on the forward solver that is a finite element model of the electrical impedance tomography system. In this work, we have developed the forward model by using a general purpose physics-based finite element modeling software, Console Multiphysics, and with respect to the classical approach of using custom numerical packages such as aidors, this has several advantages. In particular, we can easily model unconventional geometries and not only circular sensors. We can employ higher order shape function, non-isotropic materials, and for future works we can rely on the multiphysics coupling for modeling electromechanical properties of the materials of the sensor. Regarding the inverse problem, we have developed an inverse solver based on an artificial neural network model. The neural network has been trained with the artificial data obtained by the forward model. The artificial neural network model is associated to low computational cost with respect to the classical approach of the inverse problem in electrical impedance tomography sensor. And very important, we have shown the feasibility of the approach not only in simulation but also on a real prototype. The sensor is shown in this picture. It is a circular sensor made of a piezoresistive fabric. We have 16 boundary electrodes, but in this work we use only 8 of the 16 electrodes. Regarding the hardware, we have employed the adjacent drive pattern in which current is applied in adjacent electrodes. To supply current, we use a Holland current pump. We have two multiplexers to switch the point of application of the current, and all the boundary voltages are measured through a National Instruments acquisition card. The forward problem processes the conductivity and the current at the electrodes to obtain the electrode voltages. we have employed the complete electrode model formulation, which takes into account also the contact impedance at the electrodes. The main equation of the formulation are reported in this slide. In particular, we have the generalized Laplace equation on the sensor active area, in which phi is the electric potential. We then have two boundary conditions, one on the boundary outside the electrodes, this is electrical insulation. The other boundary condition is on the boundary at the electrode interfaces. Once we evaluate the electric potential, we then use this formula to obtain the voltages at the electrodes. We have implemented the forward problem in console multiphysics. We have considered a bidimensional problem with 8 electrodes. Each electrode has been described as a boundary with an integration coupling operator. We have employed an electric current physics in which the boundary condition has been considered as normal current densities. We have employed a custom mesh that has been refined at the electrodes interface, and to simulate the adjacent drive pattern stimulation, we have employed the parametric sweep of console multiphysics. At the end, we obtain 64 electrodes potential by injecting current between each adjacent electrode couple. For the inverse problem, we have trained an artificial neural network regression model. The model has 64 inputs, the electrode potential, and associated to the drive pattern, and the outputs are the conductivity variation. To train the neural network, we have generated an artificial dataset that is made about conductivity samples and associated voltage electrodes that are calculated by using the forward model. In particular, we have employed more than 10,000 samples. Regarding the conductivity, we have simulated the mechanical stimuli by using bidimensional Gaussian inclusions with random amplitudes, position, and size, and the corresponding electrode voltages have been obtained by using the forward solver and by adding Gaussian noise. First of all, we have tested our approach in simulation by using the test dataset. In all the trial, we have observed a very good accordance between the predicted and target data. The mean square error is quite low. And in this relevant example that I report in this slide, we can see an example of a reconstructed conductivity with one Gaussian inclusion. So this example here, and a worst case example in which we have 3 Gaussian inclusions. So in both the example we can see good accordance between target, so real data, and predicted, so the data obtained by the application of the neural network regression. We then have tested our approach with the real prototype. In particular, we have solicited the sensor with a slight touch of the index finger. In all the trials we have performed, we have observed that the modification of the conductivity is coherent with the mechanical solicitations. In particular, we have here 2 relevant examples. In the first example, we solicit the sensor in the center, and we observe an increase of the conductivity in the center of the sensor. We can observe the same result for this second example, in which the sensor is solicited on the side. So here I want to underline that in the case of the real prototype, we have trained the neural network for the inverse problem with artificial dataset, so avoiding the complex procedure of training the neural network with experimental data. To the best of our knowledge, our work is the first one that employ machine learning for solving the inverse problem in electrical impedance tomography tactile sensing on a real prototype. It is important to underline that only the training phase is time consuming. So we are well aware that our results are preliminary. However, our approach can be used to model or embed in the training complex issues such as complex sensor embodiments, movement of the electrodes, deformation of the sensing surface, and also contact impedance. In future works, we will study the multiphysics capability of the system, and we will also employ a sensitivity analysis to optimize the material, the sensor, and the electrodes interface.